In 1915, working out of the University of Berlin, Albert Einstein was about to change the course of history forever. He would release his paper on the general theory of relativity, a radical new way of imagining the very fabric of our reality. He mathematically combined the three known dimensions of space with a seemingly obvious yet until then overlooked fourth dimension, time. Known now simply as space-time, this four-dimensional view of the universe was so groundbreaking and precise that it completely superseded the work of Sir Isaac Newton before him. His predictions for cosmic phenomena such as black holes and gravitational waves are still being discovered to this day, and in the last 100 years since his paper was released, general relativity has really proven itself to be the backbone of modern cosmology. However, only a couple of years later in 1917, whilst trying to apply his equations, he realised that general relativity predicted a dynamic universe, one which was either expanding or contracting, but never static. Known as Bentley's paradox, this was a problem first postulated by Newton to Richard Bentley in the late 1600s. Newton felt that stars should be pulling themselves together over time due to gravity, so why weren't they? In an effort to bring harmony to his equations, Einstein added lambda, an unknown, mysterious repelling force, a cosmological constant of some kind, pervasive throughout space and pushing back on the pull from gravity, thereby allowing the universe to reach an equilibrium. But science must reach its own equilibrium with that of observational studies. A few years later, Edwin Hubble would use the 100-inch telescope at California's Mount Wilson Observatory to show that distant galaxies were moving away at great speeds, implying an expanding universe, one that was not in equilibrium, just as Einstein's equations had first predicted. Humble in defeat, Einstein made the trip to California to thank Hubble and his team for their contributions, whilst also removing the constant from his own work, claiming it to be his greatest blunder. But what not even Einstein knew at the time was that he had just accounted for one of the hidden secrets of our universe. It would take another 70 years before we realized the universe wasn't just expanding, it was accelerating, meaning something, some hidden force, was speeding it up. Einstein had factored in this force with his constant, only to remove it. And this force would later be rediscovered and reborn by modern physicists. Like a phoenix rising from the ashes, it came back with a new name, and that name was dark energy. It seems obvious to say, but important to point out, that dark energy is not matter. Not like dark matter, which is made up of particles we cannot yet see. No, dark energy is a force, something that exhibits a constant anti-gravity-like effect on the stuff around it, and we'll go more into that later. We know that it's homogeneous, meaning it exists everywhere, evenly, across the entire universe, and it appears to be an intrinsic property of space itself. Its density is incredibly low, meaning it's very weak and barely noticeable in local space. This means we can't actually physically detect it here on Earth. In fact, the only real proof we have of its existence is to look into the past and see its effects on the growing universe. Since the light we are observing from distant stars and galaxies was emitted long ago, we are essentially looking backwards in time whenever we look into space. The deeper we look, the further back in time we are seeing. Like a cosmic photo album documenting our universe's growth from its birth all the way to adulthood, these snapshots reveal the secret existence of dark energy. By observing the speed of galaxies at different distances from Earth, we are essentially able to compare the size of the universe over different snapshots in its life. This allows us to appreciate how fast it is expanding, both now and in the past. If the relationship is linear, it means it's expanding at a constant rate. If it is curved in this direction, then it shows the rate of expansion is slowing down, which is what we expected to see since the time of Hubble, due to gravity acting to pull everything in the universe inwards, thereby slowing expansion. But in 1998, when two independent projects measured the rate of expansion by observing Type 1a supernovas in very far galaxies, they revealed it was actually pretty linear, until around 5 billion years ago, when it suddenly and mysteriously started accelerating. This made very little sense at the time. Could there be some type of force counteracting the inwards pull of gravity? And why did this force suddenly start dominating 5 billion years ago? The best explanation was actually Einstein's original cosmological constant. The idea of a constant force, pushing outwards, spread completely evenly throughout the universe. Such a force, if it was an intrinsic property of space, would build up over time. And during this process, more space-time is continuously being created. Or in other words, empty space keeps creating more empty space, which is what expanding space really is. It's the continuous creation of more empty space. On a larger scale, dark energy amounts to a sort of anti-gravity effect, pushing the universe apart, with more and more space being created to fill the gaps. If we rewind the clock to the early universe, when there was far less space than there is today, then there was also far less dark energy, meaning less expansion. But as the universe grew, the amount of space grew, and so did the amount of total dark energy, until eventually we reached a tipping point around 5 billion years ago, bringing us into a new dark energy dominated era. This is when dark energy simply overpowered the rest of the stuff in our universe, causing the expansion to begin to accelerate to what we see today. It is so dominant now that it makes up around 68% of the energy in our universe, with dark matter making 27% and regular matter making a measly 5%. So if this energy is so abundant in our universe, what is it? What is it made of? Although we can somewhat theorise the nature of dark energy, its exact cause lives mostly in the realm of speculation. Even when compared to dark matter, something we also know little about, dark energy is still far more mysterious and difficult to explain. Some of the best theories we have are that dark energy is like a field that permeates throughout space-time. Some even suggest that this field could be variable over time, known as quintessence, with dark energy representing a new fifth force after the four existing fundamental forces we already know of. Another potential theory is that it is the result of quantum fluctuations. The vacuum of space is not entirely empty. It has energy and other fields. These are in constant fluctuation and often spontaneously create new particle and antiparticle pairs, which annihilate each other. If this process is somehow producing a constant anti-gravity-like effect, then we may have just found our smoking gun. Whatever dark energy is, one thing's for sure, it's here to stay. With the rate of cosmic expansion now accelerating, it's already taken over, and there's no turning back now. Like its ominous name suggests, it worked quietly in the darkness until it took complete control of our universe. From what we gather, it looks like the universe will continue to expand forever, with galaxies beyond our local group eventually being forced out of our observable universe entirely. Like reaching the final snapshots in our cosmic photo album, these wonderful distant galaxies will eventually freeze in our night sky, suspended in animation, until eventually and gradually they too will fade away into the darkness. And yet, lying there in that darkness, completely surrounding us, only one thing will remain. The very thing that caused it all. Dark energy.